All right, guys. Hey, so I posted a video with the chocolate bunny that my husband decapitated, and it occurred to me through email. Ellie caught me that I accidentally doubled the amount of carbon in the cocoa that's in the bunny. So we're gonna redo this problem together on Notability, starting with if we have the average mass of a chocolate bunny, it's 165 grams and my bunny is 93% cocoa. We want to solve for how many carbon atoms are in the chocolate bunny. So we're going to have to take a few steps to solve this problem. The first step being, okay, what percent of the mass of the bunny is represented by cocoa? And so it's 93% cocoa, and the total mass of the bunny is 165 grams. So if we multiply 0.93 times 165, we're going to get the mass of cocoa in our chocolate bunny. So the formula for cocoa is C7H8N4O2. So before we go any further, the very next thing we need to do in order to convert from mass to moles is we need to find the molar mass of our cocoa. So here's where you would need a periodic table, and you're going to go ahead and take the mass of 7 carbon atoms, which on the periodic table is 12.01 AMUs, and we're going to add to that 8 hydrogen atoms, 1.01 AMUs, plus 4 nitrogen atoms, 14.01 AMUs, plus 2 oxygen atoms for 16 AMUs. And the combined mass of our cocoa is going to be 180.19 grams of C7H8N4O2. All right. So, if our chocolate bunny is only 93% cocoa, and we know that there are 180.19 grams per every 1 mole of cocoa, we can convert from mass into moles. So that's going to be our next step in solving this problem. And we're going to go ahead and start with the amount or the mass of the cocoa in our bunny. And we're going to go ahead and convert from that mass into moles using a mole ratio. So for every 1 mole of cocoa, it is 180.19 grams. Make sense? Hopefully. All right. So in this problem, the grams of cocoa are going to cancel, and we're going to get 0.85, 0.85 moles of cocoa. Okay? And so we know that 0.85 moles of cocoa is not quite equal to 1 mole. So we can go ahead and convert 0.85 moles of cocoa into number of particles, right? Because we know that for every 1 mole of cocoa, or any substance for that matter, there are 6.023 times 10 to the 23rd particles, right? So that's the constant, that's Avogadro's number. So if we convert from moles of cocoa into numbers of particles, we'll know exactly how many cocoa particles are in our Easter bunny. So multiply 0.85 times 6.023 times 10 to the 23rd, and you get a lot of cocoa particles. It's going to be 5.12 times 10 to the 23rd particles of cocoa, which is, again, C7H8N4O2. Okay? So that's not what the question is asking us to solve for, though. It's great that we know number of particles, but if you look back at the original question, it asks how many carbon atoms are in the chocolate bunny. So in order to solve for carbon atoms, we need to look at this formula, right? So for every 1 particle of cocoa, and again, there are 5.12 times 10 to the 23rd of these, for every one of those, there are 7 atoms of carbon, right? So we're multiplying here the number of particles, which is a big number, by the number of atoms in each particle. And you're going to get, for that answer, 5.12 times 10 to the 23rd times 7. You're going to get an answer equal to 3.58 times 10 to the 24th particles, or sorry, not particles here, this is atoms, which is a particle, but so you get 3.58 times 10 to the 24th atoms of carbon. If you plug this into your calculator, I had some questions yesterday about this. You're going to get 5 times 7 is going to give you roughly 35, right? 35.84. And then obviously we're not going to drop the 10 to the 23rd off of that number. So with scientific notation, I don't know if you guys have learned this in math class or in a past science class, but with scientific notation, you have to write your number that precedes the exponent. It's got to be a number between 1 and 10. So obviously 35 is not between 1 and 10, but 3.5 is. So by moving that decimal from 35 to 3.5, we're changing the position of the decimal by 1/10 place, right? So what that means is that you need to add 1/10 place to the exponent to account for that change. So 3.58 times 10 to the 24th atoms of carbon is technically the same thing as 35.84 times 10 to the 23rd atoms. If you were to write them out, they would be the same number, but it's not correctly written in scientific notation. So the correct answer would be that answer. Hopefully that makes sense. If we were to continue this problem and solve for the number of hydrogen, nitrogen, and oxygen particles or atoms in each one of those cocoa particles, all we would have to do, guys, is change this ratio. So rather than number of atoms of carbon, if we wanted to solve for hydrogen, we would multiply the 5.12 times 10 to the 23rd cocoa particles by 8 atoms of hydrogen. And obviously that would give you a different number here. If we wanted to solve for nitrogen, we would do the same, but instead of 8, it would be 4 atoms of nitrogen. If we wanted to solve for oxygen, it would be 2 atoms of oxygen. All right, so again, sorry for those that were confused this morning. Hopefully this kind of clarifies things and gives you a correct answer in your warm-up. Again, these mistakes aren't caught easily with virtual learning. So I apologize. Thanks, Ellie, and I'll see you guys soon. Bye.